Dear students, so in previous class we discussed the limit of convergence of a sequence and the limit of certain. We found limit of certain sequences like n power 1 by n, n by n root n plus 7, etc. and so on. Now we discussed the new term. It is m-tail sequence. M-tail of a sequence. So consider that x equals sequence x equals x1, x2, etc. be a sequence of real numbers, and if m be a given natural number, m is any natural number, then the m-tail of sequence x, the m-tail of sequence x is denoted by xm and is given by xm equals sequence xm plus n, where n equals 1, 2, etc. Where n equals 1, 2, etc. means n is a natural number. That is xm, the m-tail of the sequence x is denoted by xm, and xm equals xm plus 1, xm plus 2, etc. So this is the m-tail of the given sequence x. M-tail of the given sequence x is denoted by xm. So consider the sequence 2, 4, 6, 8, 10, 12, 14, etc. Consider this sequence. So what is the, suppose x be the given sequence, then the three-tail of the sequence, x3. M-tail is denoted by xm, so three-tail of the sequence x3. Here what is x3? x3 is x3 plus 1. x3 is x3 plus 1 means x4. x4 means x3 is sequence 8, 10, 12, 14, etc. What is the two-tail? Two-tail means x2. x2 means it is sequence xm is xm plus n, where n is a natural number. So it is x2 is 6, 8, 10, etc. So this is the m-tail of a sequence. If x equals sequence xn be a sequence of real numbers and n is any natural number, then the m-tail of the sequence x is denoted by xm and is given by sequence xm plus n, that is xm plus 1, xm plus 2, etc. Okay. So now there is a result. The theorem states that x equals xn, let x equals xn be a sequence of real numbers, and for any natural number m, the m-tail xn of x, the m-tail xn of x converges if and only if xm that converges if and only if the sequence x equals xn converges. Let x equals sequence xn be a sequence of real numbers, and for any natural number m, the m-tail sequence converges if and only if the given sequence converges. That is limit x equals limit x. Limit x equals limit x. So how? So its proof is in this way. First we suppose that, consider the necessary arguments. First suppose that the m-tail sequence xm converges to x. The m-tail sequence xm converges to x. So means, then what is the nth term of xm? Nth term of xm. Nth term of xm means xm plus n. Okay. Nth term of xm means xm plus n. xm plus n means this is nth term of xm is xm plus n. That is the m plus nth term of x. M plus nth term of x means nth term of xn is xm plus n. xm plus n means the m plus nth term of x. So what about qth term of x? So from here, qth term of x is nothing but the q minus mth term of, from this argument it is q minus mth term of the m-tail sequence x. So give the, when nth term of xm is xm plus 1, xm plus n, that is the m plus nth term of x. So from here, we know that q the term of x is nothing but q minus m the term of the m tail sequence xm for all q greater than m. Okay. Now, for all epsilon is positive, sequence, first suppose that the m tail sequence xm converges to xm. That means, for all epsilon is positive, there exists a natural number k, such that modulus of xm minus xm strictly less than, the mth tail, that is xm plus n minus x strictly less than epsilon for all m plus n greater than or equals k. First we assume that the m tail sequence xm converges to x. That means for all epsilon positive, there exists a natural number k such that modulus of xm plus n minus x strictly less than epsilon for all m plus n greater than or equals, for all n greater than or equals k. Here, for all n greater than or equals k. That means modulus of xn minus x strictly less than epsilon for all m plus n, for all n greater than or equals, m plus k. Okay. This is by the definition of the convergence of m tail of the sequence. So from here, that is for all n greater than or equals k, hence modulus of xn minus x strictly less than epsilon for all n greater than or equals m plus k. Put a k dash equals m plus k. Put a some k dash equals m plus k. So what you get? This become for all epsilon positive, there exists some k dash for n, since m and k are natural numbers, such that modulus of xn minus x strictly less than epsilon for all n greater than or equals k dash. That means sequence xn converges to x. Sequence xn converges to x. So this is the necessary argument. Agreed. How to prove a reverse inclusion? So, for the reverse inclusion, first we suppose that the sequence x converges to sequence x equals sequence xn, that converges to x. For the reverse inclusion, that sequence x equals sequence xn converges to some x. That means, for all epsilon is positive, there exists some k for n, there is a natural number n, such that modulus of xn minus x strictly less than epsilon for all n greater than or equals k. That means modulus of xn minus x strictly less than epsilon means modulus of xm plus n minus x strictly less than epsilon for all m plus n greater than or equals k. That's immediately followed from that argument. That means modulus of x m plus n, that means modulus of x m plus n minus x strictly less than epsilon for all n greater than or equals k minus m. Enough. Put a k2 dash equals k minus m. Put a k2 dash is k minus m. So this becomes modulus of x m plus n minus x strictly less than epsilon for all n greater than or equals k2 dash, where k2 dash be a natural number. So that means sequence xm and xm plus n that converges to x. What is sequence xm plus n? That is the m tail sequence xm of x that converges to x. So this is the sufficient argument. So means the sequence x equals xn converges, then the x equals xn be a sequence of real numbers, then if its m tail sequence converges, if and only if the sequence converges. Agreed? Now, we consider some limit theorems. Next, we discuss about some limit theorems. What is a limit theorem? Limit theorems. Definition. So consider the bounded of a sequence. When you say a sequence is bounded, consider sequence x equals xn be a sequence of real numbers. It is bounded if there exists a real number m that is sufficiently large, a real number m such that modulus of xn strictly or modulus of xn less than or equals m for all n following n. So this is the definition of boundedness of a sequence. Yes, let x equals sequence xn be a sequence of real numbers, then secant xn is said to be bounded if there exists a real number m such that modulus of xn less than or equals m for all n following n. So for consider the sequence 1, 1, 1, etc. So the sequence is bounded. Why? Because the sequence means mod xn less than or equals 1. Okay, so instead of m here it is 1, so the sequence is bounded. What about sequence 1 by n? Sequence 1 by n. Sequence 1 by n means 1, 1 by 2, 1 by 3, etc. So the sequence is also, this sequence is also bounded. Why? Because mod xn less than or equals 1. Agreed. So you can choose the real number capital M is 1 here, then mod xn less than or equals m, mod xn less than or equals 1 means sequence 1 by n is also a bounded sequence. Now, by using this definition, we consider result. A convergent sequence of real numbers is bounded. The theorem states that a convergent sequence of real numbers. A convergent sequence of real numbers is bounded. Convergent sequence of real numbers is bounded. How? So far, this proof is come to this proof. Let x equals xn be a sequence of real numbers. Be a sequence of real numbers. Suppose sequence xn converges, means sequence xn converges to x. Sequence xn converges to x. Sequence xn converges to x means by definition it is for all epsilon positive there exists a natural number k such that modulus of xn minus x strictly less than epsilon for all n greater than or equals k. Agreed. Put epsilon is 1. Put epsilon equals 1. Then epsilon is 1 means here we have mod xn minus x strictly less than 1 for all n greater than or equals k. Mod xn minus x strictly less than 1. But we have mod xn minus mod x. Mod xn minus mod x less than or equals mod xn minus x. We already proved that in previous chapters. We have mod a minus mod b less than or equals modulus of a minus b. According to that argument, mod xn minus mod x less than or equals mod xn minus x. Mod xn minus x strictly less than 1. That means mod xn strictly less than 1 plus mod x. Mod xn strictly less than 1 plus mod x for all n greater than or equals k. Agreed. Then, for the sake of argument, put m equals maximum mod x1, mod x2, etc. Put m equals maximum mod x1, mod x2, etc. Mod x1, mod x2, etc. Mod x k minus 1, mod etc. Mod x k minus 1, 1 plus mod x. So we have mod xn strictly less than 1 plus mod x for all n greater than or equals k. Then you can construct this m is maximum of mod x1, mod x2, etc. mod xk minus 1, 1 plus mod x. Then clearly we have mod xn less than or equals m. Mod xn less than or equals m. That means the sequence xn is bounded. Sequence xn is bounded. So a convergent sequence is always bounded. When sequence x equals xn be a sequence of real numbers, suppose it is converges to x, then clearly the sequence of convergence or convergent sequence is always bounded. Convergence should imply the boundedness. Convergence should imply the convergence of a sequence should imply the sequence is bounded. So convergence implies boundedness. What about the reverse equation? Do you say that a bounded sequence is convergent? Is it convergent? A bounded sequence is convergent? Is a bounded sequence is convergent? So you consider a sequence. Consider 0, 2, 0, 2, 0, 2, etc. Okay. So is it bounded? Sure. Why? Because xn equals it is 0 if n is odd. If n is odd, 2 if n is even. Agreed. So clearly the sequence is bounded. Why? Because here there exists a real number 2 such that mod xn less than or equals 2 means the sequence is bounded. Is it convergent? No. The sequence does not converge. Why? Because the sequence does not converge. In previous class we say that the sequence x equals sequence 0, 2, 0, 2, 0, 2 etc. is not converges. Why? Because if this is converges, mod xn minus x strictly less than 1, choose epsilon is 1. Agreed. So mod xn does not converge to 0. The sequence does not converge to 0. Moreover, the sequence does not converge to 2. So the sequence does not converge. So boundedness need not be implies convergence. A convergent sequence is always bounded, but a convergent sequence is bounded, but a bounded sequence need not be convergent. Reverse inclusion need not be true. Agreed? Okay. Now, consider another result. Let x equals xn. Let x equals xn and y equals yn with a sequence of real numbers converges to x and y respectively. Converges to x and y respectively. Let C fall in R. Let C is any real number. Let C fall in R. Then the sequences x plus y, comma x minus y, comma xy and x by y. Sorry, x plus y, xy, x minus y, not x by y, and the cx. And the cx are converges to x plus y, x minus y, xy and the cx respectively. That is the first regular. Sequence x equals xn and y equals y with a sequence of real numbers such that x converges to x and y converges to y. First we prove that x plus y converges to x plus small x plus y, sequence x minus y converges to x minus y, xy converges to xy and cx converges to cx. Where c is any real. How? Later, its proof is immediate. How? Let sequence xn, x equals sequence xn converges to x. That means for all epsilon positive there exists a natural number k1 such that modulus of xn minus x strictly less than epsilon for this epsilon by 2 for all n greater than or equals k. For all n greater than or equals k. Also, y is sequence yn. Sequence yn converges to small y. Sequence yn converges to y means again for all epsilon positive there exists k2 for an n such that modulus of yn minus y modulus of yn minus y strictly less than epsilon by 2 for all n greater than or equals k. Put a k equals maximum of this k1 k2. So the result hold for these two results are hold for k. That is the first and second results are hold for all n greater than or equals k itself. Now consider what about the modulus of x plus y minus of xy, or modulus of xn plus y, simply xn plus yn minus of x plus y. It is equals modulus of xn minus x plus yn minus y. By the triangle inequality, it is modulus of xn minus x plus modulus of yn minus y. So it is strictly less than epsilon by 2 plus epsilon by 2 for all n greater than or equals k. Means finally modulus of xn plus yn minus of x plus y strictly less than epsilon for all n greater than or equals k. That implies xn plus yn converges to x plus y. So when xn converges to x and yn converges to y, then xn plus yn converges to x plus y. Similarly, you can prove that this xn minus yn converges to x minus y. How? You can consider, instead of xn plus yn minus of x plus y, consider xn minus yn minus of x minus y. Xn minus yn minus as modulus of xn minus yn minus of x minus y. That is modulus of xn minus x minus of modulus of yn minus y. That's again simply less than epsilon by 2 plus epsilon by 2 plus epsilon. Then similarly we can show that the sequence xn minus yn converges to x minus y. Agreed. So the first and second arguments are immediate. Come to the third one. How to prove the sequence xy converges to the sequence x and yn converges to xy. Means x plus y or x into y converges to xy. How? Modulus of, to prove x and yn converges to xy, that is the first and second are finished. Then come to the third one. To prove x and yn converges to xy. Modulus of x and yn minus xy. What about the modulus of xn minus yn xy? Xn yn minus xy. That can be rewrite as modulus of xn yn minus xyn plus xyn minus xy. You can introduce plus or minus, you can introduce plus xyn and minus xy and rearrange. That equals modulus of this less than or equals modulus of xn yn minus xy. Here yn is common, that is modulus of yn into xn minus x plus xyn minus xy into x minus y into x into modulus of yn minus y. Modulus of x into yn minus y.